High wire artist Carl Wallenda, possibly the world's best-known circus performer, fell to his death today doing an outdoor stunt in Puerto Rico. For that, here's James Walker.
The only place I feel alive, said Carl Wallenda, is on the wire. And there he was this morning, 73 years old, 120 feet in the air, 10 stories above San Juan, performing as he had for 58 years. The idea was to promote a circus act he was performing with his granddaughter. So, a high wire walk across the street from one beachfront hotel to another. But as he reached halfway, the ocean wind suddenly picked up, gusting to 30 knots. And Carl Wallenda, the best man in the world on a high wire, fought for his balance. "200 people saw Wallenda fall. Many rushed to help, but it was too late. Wallenda's body had struck a parked taxi. He was dead on arrival at the hospital." Carl Wallenda and his family came to the United States from Germany in 1936, brought here by John Ringling and the Ringling Brothers and Martin and Bailey Circus, which was their home for the next 18 years. It was a family act, but Father Carl was the star. Frequently, he appeared alone, like in this stunt when he walked across an 1,100-foot cable strung 700 feet above the Tallulah Gorge in Georgia. He was so supremely confident that he did it wearing a microphone to narrate his own crossing.
It's a little windy now. More wind than I expected. God is with me. I believe everything will be all right.
Carl Wallenda is the fifth member of the family to die while walking the high wire, the latest in a series of tragedies that began in 1962 with a 7-man pyramid, developed and perfected by Father Carl. During a Detroit appearance, the pyramid collapsed. 2 family members fell 40 feet to their death. Carl's son Mario was permanently paralyzed. Carl Wallenda did not escape untouched. He suffered a broken pelvis and a double hernia, but he always returned to the ring and his high wire. This afternoon, Carl Wallenda said that despite his uncle's death, the act will go on. James Walker, ABC News.
His final performance. At 73, a high wire walk 10 stories up to promote a circus appearance with his granddaughter. The patriarch of the great Wallendas was best known for the creation of their 3-level human pyramid. It was also their most dangerous act. This happened in practice. In 1962, the pyramid collapsed for real. 2 were killed and an adopted son crippled for life. Despite it all, Wallenda told interviewers he was not afraid.
Well, even in a big fall when I lost 2 people to get killed, and my son is paralyzed for life. And I never failed. And 24 hours later, I was up on the wire with a broken pelvis bone.
The Winnebago County Board.
All right, so the pole.
High wire artist Carl Wallenda, possibly the world's best-known circus performer.
All right, these tightrope walkers, they got this pole, right, that they are using. So what's the purpose of the pole? It's to balance themselves. Okay, so how did that even help? How did that even work? All right, so that's one of the things that we will focus on. All right, so when you look at the acceleration here, okay, we always pretended that this is a centripetal acceleration, the acceleration directed towards the center. But all of a sudden you realize that this thing is speeding up. So there's also a rotational acceleration involved. So this guy is experiencing 2 types of acceleration. One of them is the centripetal acceleration. The other one is the rotational acceleration. So when you have like 2 kinds of accelerations, how do you figure out what the net acceleration is, the total acceleration is? Because this thing is actually reading the total acceleration. So how do we figure that out? All right, so this is a depiction of Galileo. I think Galileo is right here. Is conducting the incline experiment. So you got this ball, it's rolling down. I think this was the first and second experiment, in-person experiment that we did. And then you guys kind of demonstrated that the rolling ball is going to accelerate uniformly. So what was the purpose of the experiment? I mean, aside from the fact that Galileo liked to play with balls for whatever reason. Right? So remember, this guy was under house arrest, he's going blind, and then that's when he starts to conduct these physics experiments that made him famous. What's the purpose of it? So the purpose of the experiment was to figure out the acceleration due to gravity. Okay, so the falling objects will accelerate under the influence of gravity, right? So you figure that everything is going to accelerate at the same rate, and then he was looking for a way to measure that acceleration. Okay, and then in order to slow the motion down, he decided to use an incline. All right, so there's a nice little story behind it that we're going to focus on. I think from PBS Nova. I'm going to go forward and then go backwards so that this releases itself.
Galileo had spent half a lifetime trying to prove the Earth moves. Now, he would come to terms with something much more basic, the mathematics of motion itself. But motion is hard to measure.
It all happens just a bit too fast for you to see what is going on. Galileo hit on this wonderful idea of slowing down the motion. So instead of trying to watch a thing falling, he rolled balls down very gentle slopes so that the speed built up very, very slowly.
Galileo reasoned that as balls rolled down slopes, they would accelerate, just as they did in freefall, but more slowly. As a young man, Galileo had designed a very accurate inclined plane, one of the most important pieces of experimental apparatus in the history of science. Galileo left behind no plans for his inclined plane, but based on his experimental notes, Professor Roberto Caparelli is using what he believed to be Galileo's original design to discover how he was able to accurately measure acceleration.
Galileo studied the inclined plane, slowing the motion of falling bodies until he was able to observe the phenomena. He was able to measure exactly how fast a ball would roll, timed with the swing of a pendulum. Galileo was sure that the steady acceleration must be governed by a mathematical rule.
So he takes this very gentle inclined plane and he lets the ball roll down and he watches how that ball speeds up and he measures how far it goes in a certain time. And then he makes his first empirical discovery that if in the first unit of time it goes 1 unit of distance, in the next unit of time it travels 3 units of distance, and in the next 5, and in the next 7. So it has this beautiful numerical progression, 1, 3, 5, 7. And he calls this the odd numbers rule. And he really is entranced by this. He knows he's made a huge discovery.
Galileo had found a mathematical rule for accurately predicting the motion of objects in the real world, a universal law which applied to any falling bodies.
Underneath this beautiful empirical law that he found a deeper law, clearly a deeper law, using mathematical logic and deductions. And this was actually the key to all the later great successes, first of Newton and then of Einstein and all the other wonders of modern science.
As a young man, Galileo had revolutionized astronomy. But at the age of 74, his last great book revolutionized the physics of motion.
From the point of view of physics, his most important contribution is his discourse on the 2 new sciences. Indeed, it's that book that provides the real foundation for Isaac Newton.
Okay, so that very briefly. All right, so the underlying assumption of Galileo's experiment is if everything falls at the same rate, does this mean that everything is also going to roll at the same rate when it was slowing down the motion? What I'm asking is this. Now, you got this block cylinder, and then you got this rim. Do you think that both of them will roll at the same rate all the way to the bottom? Do you think they will have the same acceleration? Do you think they will have the same speed? All right, so this is one of the experiments that we'll get to do. I think it's within a month or so. Oh, we gotta talk about this. This one is weird. I'm just gonna talk about it as if it's some kind of an ordinary concept from physics. It's not. And there's a backstory that I'm gonna talk about later on, not today, but some other time, which makes it really fascinating. All right, so you got this falling chimney, and these chimneys usually break somewhere in the middle. Okay, so like 9 out of 10 times they will break. So the question is why, and why does it matter? Okay, the reason why it matters is because there's a concept in physics which is so well concealed in this observation, and when I'll point it out, you will go, oh, now that makes sense. Okay, so let's entertain ourselves just watching a bunch of chimneys just falling down. And it's just that's the first one. All right, this one was fighting it nicely, but ended up. This doesn't count. It didn't really. All right, so I want to see it fall sideways, and when it's falling sideways, it'll break off at some point. So the question is where, and the next question is why. Oh, it just broke off right there. That's nicely done. Okay, let's check to see if there's more. Oh, wait, no, we got more. All right, so we got both of them falling. All right, now this one was weird. Okay, I know the reason why this didn't break. Okay, so this is worthy of a discussion. Okay, it'll make sense when we get to it. So they put some weights here. That is really clever. They didn't want these things to break off. This is an interesting engineering design. All right, they put tension. And this is, oh damn, this is clever. I think this is from Russia. They didn't want this stuff to break off. They just wanted to bring it down, straight down. Done a good job with that. That's weird. So let's check this out. It's a pretty nice solid structure. I'm very surprised that eventually it's probably reinforced from this side. All right, it's gonna give and right there and end up breaking. And this one is huge. Oh, you can see it. It just broke off right there. Right. Okay, so I think we've seen enough. Okay, so it kicked me out of PowerPoint, so let me just get back to PowerPoint. Okay, okay, so we're right here. Okay, so let's talk about the angular quantities. Okay, so rotational motion. The first one is the angular displacement. It's the same as regular displacement, except this is taking place in the rotational motion. Angular displacement means angle. That's it. This is the angular displacement. So this thing is going to get displaced angularly, rotationally in this direction. So that's the angle known as the angular displacement. Proper unit is radians. 2 pi radians is going to be 360 degrees. And 1 revolution is going to be 2 pi radians. So 1 revolution, 2 pi radians, which is 360 degrees. That's all you need to remember from this section. All right, so the angular displacement is the angle. Angle is going to be expressed in terms of radians. And so 2 pi radians is 360 degrees, and 2 pi radians 360 degrees is the same as 1 single revolution. All right, so pick out the best answer and place it in the chat. All right, so you guys got it. B is the best answer. All right. And then we got angular velocity. All right, so the angular velocity is how fast the angular displacement changes in time. All right, so here's your initial angular displacement. So you go from this angular displacement to that angular displacement within a certain time period. So how fast your angular velocity, how fast your angular displacement changes in time. How fast the measured angle changes in time is your angular velocity. All right, so angular displacement is going to be radians per second. Angular displacement is going to be radians. The angular velocity is going to be radians per seconds. All right. I think there's one more thing that I need to specify. All right, so for angular motion, we're using Greek letters. So you got theta for the angular displacement. What looks like W is omega. So omega is the angular velocity. All right, so pick out the best answer. Angular velocity, I'm going to go 30 more minutes. All right, so B is the best answer for that one. The next one is the angular acceleration. So that's how fast the angular velocity changes in time. All right, so here's your initial angular velocity. Here's your final angular velocity. So how fast the angular velocity changes in that direction. Alpha is your angular acceleration. All right, so angular acceleration is going to be radians per second squared. Angular acceleration is, all right, so the radians per second squared. All right, so let's take a look at the problems using this. All right, so everything that we've done the first couple of weeks, we'll just repeat the same sort of stuff for angular motion in essence. So we got the blades in a blender. Okay, so initially they're rotating at this rate, which is 65 RPMs, revolutions per minute. And then you turn off the engine, and the blades will come to a rest. They will come to a stop within 3 seconds, right? So what's the angular acceleration of the blades? So they're going at 6,500 RPMs. Within 3 seconds, they're not moving. So they'll come to a stop. So that's what we got. So you got 65 RPMs. So they'll go from 6,500 RPMs to 0 radians per second in 3 seconds. What's the acceleration? Okay, the only thing which is kind of tricky regarding solving these problems is not the math itself so much, it's the conversions. Because we will have to do the conversions to the radians per second squared and all that stuff. So you cannot use degrees, you have to use radians. And in real life, use RPMs, revolutions per minute. So revolutions per minute needs to be expressed in terms of radians per second. So remember, 1 revolution is going to be 2 pi radians, and 1 minute is going to be 60 seconds. So, and then you do the multiplications, the conversions, you end up getting a number in terms of radians per second. Okay, so when you're watching the lecture like this, it's fairly easy. You see it, you understand it, you get it. But when you try to do it on your own, all of a sudden you realize that there's something missing. If you're not careful, you're not going to be able to generate this number. The emphasis should be put on this pi, 2 pi radians. The pi, for pi, you have to use the irrational number 3.14 in order to generate this number. All right, so when you see a pi, when the numbers are expressed in terms of radians, make sure that you're using the actual number for pi. So the approximation is 3.14. All right, so that's something for you guys to highlight and remember. Okay, the rest of it is straightforward. So it goes from this speed to that speed, 6,500 RPMs to 0. All right, and so all of a sudden this is where you're at. All right, so you plug the numbers in, and then we are done. So it's going to give you the acceleration in terms of radians per square seconds, second squared, or whatever. Okay, so now we will have to take the angular variables, and then we will have to express these variables along the direction of the curvature that you're looking at in terms of things that we can measure directly. All right, so here's your angular displacement. So when there's this amount of angular displacement at this radial distance, how much of a linear displacement is going to cost? What is the length of this curvature measured in terms of meters, centimeters, millimeters, inches, feet, yards? It doesn't matter. Okay, so this is the stuff that you can directly measure. So what is the length of this curvature? So the length of this curvature is known as the arc length. So you're measuring the length of the arc that you got there. All right, so if you know the angle, so here's your angular displacement. If you multiply it by the radial distance to that point, it's going to give you the arc length, the length of the curvature that you're looking at. Likewise, if you know the rotational speed, all right, so this is the rotational velocity, you can figure out the speed along the direction of the curvature, which is known as the tangential speed or tangential velocity. Tangential means that your vector or your line is going to touch the curvature at one point, but it's not going to cross. So it's going to be touching the curvature. So it's always going to point in the direction of the curvature that you're looking at. So that's the speed along the direction of the curvature. That's the linear speed along the direction of the curvature, which is known as the tangential speed. All right, once again, if you know the rotational speed, if you're interested in the speed that is given at a certain radial distance away from the pivot, the point of rotation, all right, the only thing you have to do is just take this rotational speed and multiply by the radial distance. As a result, you can figure out the speed in the direction of the curvature, otherwise known as the tangential speed. Okay, likewise, if you know the acceleration, rotational acceleration, you can figure out this rotational linear acceleration in the direction of the curvature, along the direction of the curvature. All right, so the acceleration, linear acceleration in the direction of the curvature, is known as the tangential acceleration. So you got the rotational acceleration at this radial distance. It's going to give you the acceleration in the direction of the curvature. All right, so the angular terms are on the right-hand side. If you multiply any of the angular variables by the radial distance, it's always going to give you the tangential variables or the linear variables. All right, so here's the length of the curvature, the arc length. This is the speed along the direction of the curvature. That becomes the tangential speed. There's the acceleration along the direction of the curvature. That's known as the tangential acceleration. All right, so that's it. So the linear expressions that you're looking at, the arc length, the speed, the acceleration, will be expressed in terms of meters, seconds. So it's going to be meters per second squared, and so forth. All right, so pick out the best answer. Okay. All right. So what do we have? We got a boy and a girl riding on a merry-go-round, and this thing is turning at a constant rate. All right. So what do we know? The boy is going to be near the outer edge, and the girl is closer to the center. Who has the greater angular displacement? Which means that which one is going to be at a greater angle? To answer that question, both of them will be at the same angle, right? So C is the best answer for this one. So C is the best answer. All right, so horses that move at the fastest linear speed on a merry-go-round are going to be located at the outer edge, right? So larger the radial distance is, the faster they will move. So he's the best answer for this one. All right, so I think everybody's done. Okay, so which one is going to have a greater angular speed? Angular speed is going to be the same for both of them. Because angular speed does not depend on the radial distance. Angular speed depends on how fast the angular displacement changes in time, how fast the angle changes in time. So the angle is going to change in time at the same rate for both of them. So which means that both of them will have the same angular velocity. Okay, what do we have? Okay, so we got a rotating rigid body. So which statement is the most accurate statement? The center of rotation is the center of gravity. Well, maybe not. But that's a debatable answer, so I don't care about that. So all points on the body are moving with the same angular velocity. All points on the body are moving with the same linear velocity. Not all points on the body will be moving at the same linear velocity because the linear velocity depends on the radial distance. So C is not the best answer. The center of rotation is at rest, not moving. Its center of rotation is at rest. It may be correct, but I'm not interested in that either. I think the best answer is what we were going for. So the best answer in this case is all points on the body are moving with the same angular velocity. So angular velocity is going to be the same for all of them. D is the best answer for this one. Okay, so we got a bicycle. Diameter of the tires given in terms of centimeters. Travels 8 miles. That's about 8 kilometers. That's about 5 miles. So how many revolutions will it take for the wheels to actually travel that distance? All right, this is more of a multiple choice quality test question. All right, so diameter is twice the radius. So centimeters expressed in terms of meters, move the decimal to the left by 2 decimal places. All right, so the radius is going to be half the diameter, so we got our distance. All right, so the S is going to represent the total path that the wheel is going to take. It's going to be 8,000 meters. So how many revolutions does it take? So the first thing we need to do is just figure out the angular displacement in terms of radians, and then convert that to revolutions. All right, so the equation that we will get to use is the arc length equation. Solve for the angular displacement. Get the answer in terms of radians, and convert this to revolutions. So once again, for pi, you have to use 3.14. So it's going to take about 4,000 revolutions to travel about 5 miles. All right, so there are 2 types of accelerations at work here. Notice that this is speeding up, so which means that there's rotational acceleration. And because it's circular motion, there's also centripetal acceleration. So how do you figure out the total acceleration if you have 2 different accelerations at work? How does that go? All right, so we will have the centripetal acceleration, and then we'll also have the tangential acceleration. So we got 2 types of accelerations. Our centripetal acceleration happens in rotational motion when this thing is moving at a given speed, so it's got tangential speed right at that point. So this tangential speed is going to be responsible for the centripetal acceleration that you got. Here's the generic formula that we've been using forever. So square of the tangential speed divided by the radius is going to give us the centripetal acceleration. We can express the centripetal acceleration also in terms of the rotational speed, not only the tangential, but also the rotational speed. So you got the rotational velocity times the radial distance is going to give you the tangential velocity. So do a back substitution. And then just cancel out the like terms. So you got a square, you got r, so they will cancel out. So the centripetal acceleration can be expressed in terms of the tangential velocity as well as the rotational velocity. Okay, so whichever is available, but this is relevant in terms of the multiple choice test. Be able to do the conversions from rotational motion to linear motion and vice versa. All right, and then we got the rotational acceleration. All right, so now you got the rotational acceleration right after that. So the motion, if it's got rotational acceleration, the rotational acceleration can be expressed in terms of tangential acceleration. So you got centripetal acceleration because there's speed at every single point, and at the same time, it's speeding up in this direction. So which means that it's got tangential acceleration. So if that's the case, how do you figure out the total acceleration? Okay, so now you're dealing with vectors, obviously. You cannot get to total acceleration by adding this to that. So you will have to do a vector addition. Something that you end up learning in Calc 3. All right, and obviously most of you guys are not taking Calc 3. So let me just tell you how it is done. Okay, so with vectors, you're free to move the vectors anywhere you want on this page. The only thing that you cannot do is you cannot change the size of the vector, and you cannot change the direction of the vector. All right, so these vectors will always point in the same directions, and they will always have the same magnitude. So you cannot change the size, you cannot change the direction, but you're free to move these vectors any way you want. And so what I'm going to do is I'm going to move these vectors in order to make a right-angle triangle. All right, so welcome to calculus, Calc 3. So I'm looking for the total acceleration, and I'm going to make a right-angle triangle by using these vectors. All right, so the base of the vector is going to be centripetal acceleration. The height of this vector, I'm going to move this way. It's going to become the tangential acceleration. And the hypotenuse of this triangle is going to give me the total acceleration. That's it. All right, so the Calc 3 is the same as trig in this case. All right, so the hypotenuse is what you're looking for. So the hypotenuse of this right-angle triangle is going to give you the total acceleration. That's it. All right, so in circular motion, if there's constant speed, if there's no tangential acceleration. So circular motion at constant speed, the centripetal acceleration always points towards the center. But if there's also tangential acceleration, it's not going to point towards the center. It's going to be in an angle relative to the center. So we can figure out the direction of the acceleration relative to the centripetal acceleration. If you know the base as well as the height of this triangle, obviously you can use the tangent of the angle. So you can take the inverse of tangent of both sides, inverse of tangent of both sides. As a result, you can isolate the angle on the left-hand side. And that's it. All right, so that's going to give you the angle of the total acceleration. So when these guys pilots are in training like that, when there's that sudden onset, okay, so when they start to throttle this thing up, acceleration is not pointing towards the center usually. It's coming at an angle, so it pushes the blood towards the side of your head, towards the back of it. So that's also going to be a trying experience. Okay, trying to handle that. So the blood is going to start to pull towards the back of your head, but it's going to be towards the side of it. All right, that's going to cause even bigger disorientation under the circumstances. All right, so once again, the centripetal acceleration can be expressed in terms of the rotational velocity, and the tangential acceleration can be expressed in terms of the rotational acceleration. And these terms will go into the formulas that we came up with previously. All right, let's take a look at problem number 3 from the handouts. Problem number 3. All right, so we got a rotating merry-go-round. So a single revolution is going to take 4 seconds. So the question is, what is this linear speed of a child seated about 1.2 meters away from the center? And what's her acceleration? Give the components. Okay, so this is more exercise than an actual physics problem. So the only thing that I'm going to do is, I think I'm probably going to do A. I'm not sure if I get to do B. It's a nice little exercise so you can see how the convergence usually takes place. So 1 revolution is going to take 4 seconds. So what's the tangential speed of this kid? Seated 1.2 meters from the center. That's about close to 3 feet. And what's the acceleration? All right, if it's a constant speed, if it takes 4 seconds, 1 revolution, if it's a constant speed, the acceleration, there's going to be a centripetal acceleration. All right, so what's the tangential speed? Explain that. So what I'm going to do is I'm going to use this formula. First thing I'm going to do is figure out the rotational velocity. All right, so we need to figure out the rotational velocity first, which is how fast the angle changes within a certain time period. So 1 single revolution that we got is going to be 2 pi radians per second. So we'll have to do a back substitution. And that's it. So we got everything that we need. We know the radius, we know the angle, we know the time. So it's going to give us the tangential velocity. So you plug the numbers in. So it's going to be 1.2. This is 2 pi radians. Again, pi is going to be expressed in terms of its number. It's going to be 3.14 divided by time. So the time is 4 seconds in this case. So it's going to give us a number in terms of meters per second converted to miles per hour. You end up getting about 4 miles per hour. Okay, so this was a simple exercise. So I decided not to do B because it's something that you can do yourself. Not that complicated. All right, so this one is interesting. Problem number 4, once again, it's a bit of an exercise, multiple choice quality, not a show work quality. So we got a wheel, its diameter is given, and we know that it accelerates uniformly. So it's going to go from 130 RPMs to 280 RPMs in 2 seconds. Let's figure out the angular acceleration, and then let's figure out the radial and the tangential components of the linear acceleration. At the edge of the wheel, 2 seconds after it started accelerating. Okay, so it's going to go from 130 to 280 RPMs within 2 seconds. Figure out the angular acceleration, and then look at the radial and the tangential components. Okay, let's check to see how much of it I've done. All right, so the diameter is given. So the radius is going to be half of that. All right, so the initial angular velocity is 130 RPMs. The final is going to be 280. So this thing is accelerating. All right, so the RPMs will need to be expressed in terms of radians per seconds. All right, so we're done with that. And part A, figure out the acceleration, rotational acceleration. And then part B, figure out the tangential acceleration. Oh, okay, 2 seconds later. And then look at the centripetal acceleration 2 seconds later. So it's going to have a tangential acceleration 2 seconds later. And it's going to have a centripetal acceleration 2 seconds later. All right. Okay, so the wording of this problem suggests that this is a uniform acceleration, which means that we have to use the uniformly accelerated motion formulas. All right, I'm not going to make a big deal out of it right now. Okay, so the only thing I'm going to use is I'm going to use this formula. So change in angular velocity in time is going to be the acceleration. And we know the rotational speed is going to go from this value to that value. All right, so we got the rotational acceleration. This is, once again, this one is a multiple choice quality question. All right, now we can figure out the tangential acceleration. If you know the rotational acceleration multiplied by the radial distance, it's going to give you the tangential acceleration. All right, so we got that value. And then now we can figure out the centripetal acceleration. So, all right, so this is the formula that we could use. 2 seconds later, this thing is going to be moving at this speed. So that's the rotational speed. All right, so I'm going to use this portion of the formula. So if I know the rotational speed 2 seconds later, and which we do in terms of radians per second, so I'll just multiply these two expressions. So it's going to give you centripetal acceleration. All right, and then you can find the total acceleration at that point, but I don't think that's what the problem is asking for. Oh, I mean, evidently I decided to do it anyway. All right, this is happening during a lecture. All of a sudden I'm thinking, you know, this book problem is lacking something. All right, so let's find the total acceleration. All right, so if this were a show work test problem, obviously I would want to say how these vectors come together. So obviously we end up forming a right angle triangle, and then we're looking at the hypotenuse of that thing. So this would be the total acceleration of the system. And if we know the total acceleration, it would be nice to get the angle as well, but it's happening during a lecture, and evidently I'm not interested. All right, so problem number 5. We've done the problems up to this point, so let's move on with the problems from this point on. So we got a car engine, which is slowing down. It's going from 4,500 RPMs to 1,200 RPMs in 2.5 seconds. So calculate its angular acceleration, assume constant, and then total number of revolutions that the engine makes within this time period. So it's going from 4,500 RPMs to 1,200 RPMs. It's going to take 2.5 seconds. We will assume that the acceleration is constant. We'll figure out the rotational acceleration, and then figure out the total number of revolutions that it's going to make within that time period. All right, so the first thing we'll do is list everything. So here's your initial RPMs, revolutions per minute. Final RPMs, once again, revolutions per minute. Takes 2.5 seconds. Figure out the rotational acceleration in terms of radians per second squared. And then figure out the number of revolutions it takes for it to go from that to that within 2.5 seconds. So which means that we will have to worry about the angular displacement. Okay, the only complicated thing up to this point, if it's complicated at all, is the convergence. Revolutions per minute, RPMs is what we use in the United States. So in physics, we will have to express everything in terms of radians per seconds. All right, so One revolution is going to be 2 pi radians. Okay, so for pi, don't forget to use 3.14, or else it's not going to work. 1 minute is going to be 60 seconds. That's it. So that's how we'll do the conversion. All right, so this is what's given. Basic formula was given. The only formula that makes sense to use is this one. All right, so this is not going to require a lot of thinking. This is more of an exercise, so that I want you guys to know how to use the formulas. This is multiple choice test problem. All right, so we don't have any zeros. All right, so which means that we have to isolate alpha. We do a little bit of algebra, obviously, and get to that t, and we're done. All right, so that's as far as the math goes. Now plug the numbers in terms of radians per second divided by seconds. So it's going to give us a number in terms of radians per second squared. All right, so next question is the number of revolutions. The first thing we need to do is to express this in terms of radians and then convert it to revolutions. So theta, the first formula's got theta in it, the last formula's got theta in it. So whichever the one you want to use, that's fine. I'm going to pick the first one because it's easier. All right, so theta is already on the left-hand side, so there's not much work to do. All right, the rest is just plugging the numbers in and then crunch the numbers. It's going to give us radians. So now radians to revolution. So 2 pi radians is going to be 1 revolution. So that's going to give us about 120 revolutions. All right, so this one is straightforward. That was another exercise.
Here at the Vita Corporation Flight Simulation Lab in Warminster, Pennsylvania, Dr. James Winery and other researchers are using a centrifuge to reproduce high-speed flight conditions. They hope to better understand the effects that G-forces have on the human brain.
That's it. You're going to have to really strain that, Rob. He's really going to maneuver.
This video of Winery, recorded in 1985, dramatically illustrates what happens when pilots experience a blackout episode.
First thing that happens is blood flow begins to be reduced to the head. So you begin to develop a tunnel vision. The next thing that we see is loss of motor control, loss of sensory input, complete loss of consciousness.
So right there. This froze up and then you just. Okay, this one is a little bit more interesting. Okay, this is a bit of an exercise, but this requires a little bit of thinking as well. This is almost like college physics level, as opposed to university. All right, so that guy was inside a centrifuge. So we got this centrifuge. It takes 1 minute to turn for 20 revolutions. So it's going to take 1 minute for 20 revolutions before reaching its final speed. All right, so it takes 20 revolutions before reaching its final speed. So what's its angular acceleration? Okay, so the assumption that it's constant. So what's the final angular speed in terms of RPM whenever it reaches its final speed? All right, so 20 revolutions, 1 minute. So what's the acceleration? Assume constant. And what's the final speed in terms of revolutions per second? Or RPMs, revolutions per minute. Okay, so 1 revolution is going to be 2 pi radians. So that's how many radians? 1 minute is going to be 60 seconds. We'll worry about it later. Highlight these. All right, the initial velocity is going to be 0. So this is the one. All right, this is 0. So this is the one we get to use. So isolate alpha. Initial speed is 0, so that term drops out. All right, so we came up with an expression for the angular acceleration. Time is going to be 60 seconds. Plug the numbers in. All right, so the expression is going to be radians per second squared. All right, so part A is not bad. So let's come up with part B. So how fast is it moving in terms of RPMs in reaching this final speed? So you can either use this one or that one. All right, so use this one or that one. Either one you can use, not a big deal. So I end up picking this one because it's less work. Initial speed is 0, got the acceleration, and that's it. Once again, this one is multiple choice quality, radians to revolutions, minutes, seconds to minutes, and number, it's 40 RPM. I'm not interested in 7. It's not. Let's move forward. It's not that complicated, but these exercises are becoming somewhat mindless. Just want to move on to something which is a real physics problem. All right, so displacement is the shortest distance between 2 points with the final location indicated as an arrow. Angular displacement is the angle expressed in terms of radians. Average speed is measured distance over measured time. All right, so measured distance over measured time. Average rotational speed is the measured angular displacement over time. Proper units is going to be radians per second. Average acceleration is how fast the measured velocity changes in time. Average rotational acceleration is how fast the measured rotational velocity changes in time. Arc length is the length of the curvature. And you can figure out the arc length if you know the rotational displacement, angular displacement. So only thing you have to do is take the angular displacement, multiply by the radial distance to the point at which you're trying to figure out the arc length. Tangential speed is the speed along the direction of the curvature. You can figure out the speed along the direction of the curvature if you know the rotational speed, and if you know the distance to the point at which you're interested in the rotational speed. This one is kind of interesting. Question number 13. This is also a test question. So speedometers are configured to read the rotational speed. All right, speedometers will read the speed proportional to the rotational speed. What that means is they will actually are configured to read the rotational speed, and then they multiply that rotational speed, which is omega, by the standard size of your tire, standard radius of your wheel, right? Because the cars come with standard wheels, wheel radii or size. All right, so they are going to read the rotational speed, and then this thing that you see on the speedometer also gets multiplied by this standard radius for the wheels that the car has, and as a result, it puts the number on the speedometer that you're looking at. All right, so if you're using larger wheels, what that means is the speedometer reading is going to be the same because the speedometer only reads omega that you're looking at. It just reads the rotational speed. And what that means is the car is going to be moving faster than what's on the speedometer. All right, so if your wheel size is larger than what's considered standard, and if you're thinking that you're going at the speed limit, and all of a sudden if you get pulled over, you may end up getting a ticket. That's what it means. All right, so which means that the car is going to be moving faster than what's on the speedometer. All right, so it reads the rotational speed, which is omega, and it's configured to read speed proportional to the rotational speed, which means that it's going to be proportional to the rotational speed by r, that's the radius, and it uses a standard radius for that car, and based upon that, it's going to put out a reading on the speedometer. If you're using larger wheels, the car is going to be moving faster than what's on the speedometer. All right, so that's one of the things that you have to be aware of for the test. All right, so the tangential acceleration, if you figure out the tangential, it's the acceleration on the direction of the curvature, on the direction of the curve. If you know the rotational acceleration, you multiply by the radial distance, it's going to give you the tangential acceleration. If an object has both centripetal and rotational acceleration, it's going to have a centripetal as well as tangential acceleration. If that's the case, you do a vector addition. You take the vectors, make it triangle, right angle, triangle, and find the hypotenuse of that, and that's it. So question number 17 is the case that we're looking at. We got a pilot being exposed to 12 Gs. This is a test run. Centrifuge is speeding up. That 12 Gs is going to represent the total acceleration. All right, so linear motion is made predictable by fixing the acceleration. Rotational motion is made predictable by fixing the rotational acceleration. Inertia is the tendency to retain units of motion or resistance to change of motion. And you get that tendency or resistance to change of motion, tendency to retain or resistance to change of motion from mass. Moment of inertia is the rotational inertia, something that we'll dive into shortly. All right, so this is the rotational inertia. All right, let's skip around. Let's focus on the stuff that we already know. All right, so potential energy is the stored energy. If it's gravitational, it depends on the height for a given mass. If it is related to the spring, if it's related to the restoring force, like the spring mass system, it's going to depend on the compression or elongation relative to the unstretched position or equilibrium position. Kinetic energy is the energy of motion for a given mass, depends on the square of the speed. Mechanical energy is a combination of kinetic and potential energies. Conservation of mechanical energy is the constancy of mechanical energy. Mechanical energy will be constant or conserved if the force in question is a conservative force, like gravitational force or restoring force. All right, that's it. So that's the fast review. All right, so here's an introduction of rotational force that we will emphasize during the next lecture. This is chapter number 10 lecture, I think. Chapter number 11 is going to be related to that. All right, so you got the force acting on this mass. Force causes acceleration, right? Except this mass that you're looking at is rigidly attached to this point. All right, so this force is going to cause a rotational motion. So this force is going to cause a rotational acceleration. So this is known as a rotational force. Instead of saying rotational force, we call it a torque. All right, so we use the Greek letter T, tau, for that purpose. All right, so the force times it's the radial distance to the point of rotation is going to give you the torque. All right, so I'm just changing the expression FR or RF. Either way, it works fine. All right, so what if the force is coming at an angle? If the force is coming at an angle, it's going to have two components. It's going to have a component which is going to be parallel to the radial direction. Our direction is the radial direction. And then it's going to have a component which is going to be perpendicular to the radial component. All right, so here's the perpendicular component of this force. All right, we'll call this the tangential component because obviously this force is going to be responsible for the torque, and then because this mass is rigidly attached to this point of rotation, that this is going to cause a spin motion, rotational motion. All right, so this would be the tangential component of the force. So we call it the tangential force in this case. So this tangential force times the displacement of this force relative to the point of rotation is known as the torque. So the tangential component of this force is going to be F times sine of the angle, theta. All right, and then we can do a back substitution. So the tangential component of the force is going to be responsible for the torque. All right, so this will become the complete equation for two-dimensional torque that we got. So the tangential component of the force is going to cause a tangential acceleration. Tangential acceleration could be expressed in terms of the rotational acceleration. We'll do a back substitution. And this tangential force can be expressed in terms of the rotational acceleration. So we'll do a back substitution to the torque equation there to come up with a generalized expression for torque. I want you guys to focus on R, the radial distance. All right, so this is going to give me an R squared. So you got mR squared times alpha. And then at this point, we'll just stop just briefly and then consider the following. Look, this is the linear force, and here's the rotational force. All right, so what is a linear force do? Linear force acting on this mass will cause it to accelerate. Tangential force acting on this mass-like term right here is going to cause a rotational acceleration. Okay, so you got a mass and you got a rotational mass-like term. mR squared is like mass, except it's a rotational mass-like term. So R is going to represent the location of the mass relative to the point of rotation in this case. All right, so this is a rotational mass-like term. This rotational mass-like term that you're looking at is known as rotational mass. I'd say, okay, I'd like to say rotational mass-like term instead of saying rotational mass. Rotational mass is not an accurate way of saying it. So we call it the rotational inertia or moment of inertia. All right, so rotational mass-like term is what I meant to say when I say rotational mass, because rotational mass, as is not the right way of saying it. So it's mass-like term because there's R involved. All right, so R is going to represent the distance to the point of rotation of that mass. So it's known as moment of inertia. Moment of inertia means the rotational inertia. All right, so generic expression for the moment of inertia is I, all right, which is mR squared. It's a generic expression. So you got this mass, which is going to be located at radial distance R from the point of rotation. So it's going to have a moment of inertia, rotational inertia. So moment of inertia or rotational inertia will mean the tendency to retain rotational motion or resistance to change in rotational motion. So you can look at it either way. So all of a sudden, this torque or rotational force can be expressed in terms of rotational mass times the rotational acceleration. Linear force acting on this mass will cause an acceleration. Rotational force acting on this rotational mass is going to cause it to accelerate rotational. So this and that will be equivalent expressions. All right, so what else do I want to say? All right, the only thing that I wanted to express was moment of inertia. All right, so moment of inertia. Torque is something that we will discuss during the next chapter or so. Do I care about that? Okay, no. Okay, so I'm just gonna, I think I'm gonna go forward. A couple of things that I'm gonna emphasize here. Generalized formula. Okay, so that's on the formula sheet. All right, moment of inertia requires a little bit of expression. So if you have multiple masses, you can sum up the moments of inertia for these masses. All right, so let's focus on that expression now. If you got multiple masses, you can just sum up the moments of inertia of these masses. All right, this is something that I want to emphasize. All right, so moment of inertia depends on where the rotational axis is as well. All right, this is bit of an exercise. So you got two masses rigidly attached to each other. So what I'm going to do is I'm going to rotate this mass system relative to the first mass. So rotational axis is going to be located here. All right, so it's rotating relative to this rotational axis. And then what I'm going to do is I'm going to look for the total moment of inertia of this system. Write this out. The first mass is radial distance to the point of rotation. Second mass is radial distance to the point of rotation squared and squared. All right, so the first mass is here. It's right at the point of rotation, so R1 is going to be 0. Okay, second mass is here. Its distance to the point of rotation is going to be R2, so let's just keep that. Let's assume that the distance between these two is L, or length. All right, so this gives us a generalized expression for the moment of inertia. Okay, so let's grab the second case. This time I'm going to put the moment of inertia. This time I'm going to put the axis of rotation in between, in the middle point somewhere, right there. Okay, now let's take a look at the moment of inertia of this system. Once again, just write out the expression so we can sum up the moment of inertia due to this one plus that one. And R1 and R2 will be the same. And then it's half the length. All right, and then M1 and M2, let's pretend that they're the same masses, so they become, both of them become M. So, which means that we can just add up these two terms, and R is going to be L divided by 2 and simplify the expression. And then we end up coming up with the moment of inertia. Okay, now let's stop and then think about the meaning of what we found. Notice that when you place the moment of inertia, let's say it wrong. When you place the rotational axis right in the middle between the two masses, the moment of inertia goes down by 1/2. So what does it mean? That means that its tendency to retain its rotational motion is decreased by half, which means that its resistance to change in motion is also decreased by half. That's what it means. So you got two masses, and the moment of inertia is going to depend on where you place your rotational axis. All right, this is a bit of an abstract discussion, but hopefully it'll take some meaning at some point. All right, so the tightrope walkers, they carry poles to balance themselves. So how does that help? Okay, so I got different moments of inertia. The moment of inertia is going to depend on the geometry and the shape. Okay, I think I said the same thing twice. All right, so I got a table of moments of inertia, moment of inertia of different shapes that you got. The one that we will be focusing on for this particular argument is the long uniform rod. All right, so, and the tightrope walkers tend to hold it right in the middle. All right, so the axis of rotation is going right in the middle. That's the case that represents the moment of inertia of this. All right, in this case, the moment of inertia represents the resistance to change in rotational motion. So more massive it is, the more resistance it's going to offer. Every time you lose your balance, you're just going to lean into it. And this is going to offer a lot of resistance to rotational motion, rotational acceleration. So obviously you need a pole which is relatively massive, and you need a pole which is relatively long. All right, so that's the reason why they got these long poles when these people are walking, and then these poles are relatively massive as well, and that's how they retain their balance. All right, so having said that, this is your introduction to this table that you're looking at. All right, so the things that I want you to focus on. If you got a bicycle tire, thin hoop, all right, so moment of inertia is going to be mr squared. Make sure when you're taking the test, make sure that this table is available. I should flip this table up if I haven't already. I should have a link available so that you guys have it available. If you have a book, the books have these tables. All right, so the ones that you need to know is the hoop is the one that you need to know. Solid cylinder, notice that's going to be 1/2 of this one. Uniform sphere is going to be 2/5 of mr squared. All right, once again, the point of rotation is going to be at the center of each and every single geometry. So the standard ones are, you got the hoop, you got the solid cylinder, you got the uniform sphere. These are the ones that you need to know. And for our discussion purposes, we will also look at this uniform rod through one end. All right, so we will be focusing on this one. So if the axis of rotation is right at the end, notice that moment of inertia goes down quite a bit. No, it goes up quite a bit. It doesn't go down quite a bit. This is 1/3, and this is 1/4. Okay, so that's what we got. So that we need the sphere, and this is the last one that we need to have for our discussional purposes.
Let's do this, baby.
Thousands of people packed the streets below to see Nick Wallander complete the walks 50 stories up in the air. His father was in radio contact, occasionally offering some helpful advice.
Nick, if you get a chance, give it a bounce one time so I can watch the reaction. It's moving, Dad. I'm not going to give it a bounce. All right.
This first walk on a 70-foot incline was broadcast with a 10-second delay in case anything went wrong. It took him under 7 minutes to make it across.
There we go. First down. God be the glory. I think you probably saw me shaking like a leaf. That wire was shaking underneath me, and I just wanted to make it to the other side. I wasn't going to think twice. I was getting on the wire. I'm going. So I need everybody to be nice and quiet for me, okay?
Shortly after, he did the whole thing again, blindfolded, and this time in just over a minute.
3 feet. One more step. Grab it.
The crossing saw him set 2 world records.
Love you guys.
That was cute. All right, so this guy is Nick Holanda, the grandson of the guy who, in the original clip that you guys saw in 1970s, his grandfather is the one who fell to his death. All right,
Let's do this, baby.
Thousands of people.
They did this live on TV. Obviously, there was a few second delay. The first one was a test run. This was done in Chicago. I think it was about 10 years ago. And the second run on the way back, once he figured out the conditions, he was blindfolded. And it took him a couple of minutes. The first run took like 5 minutes almost. The second walk took fairly fast. He was blindfolded on the way back. All right. Rotational inertia. The moment of inertia is, I don't want to say it's tricky, but it requires you to be slightly careful because you got two masses, and both masses are equal. All right. So, which means that they will have the same inertia. So they will have the same tendency to retain their initial motions, and they will have the same tendency. They will have the same amount of resistance to change in motion when there is a force applied. So they will resist any sort of acceleration in masses. All right, but the moment of inertia, despite the fact that the masses are the same, it's going to depend on the square of the distance, the square of the radius, in essence. So this has a much larger radius, meaning that this is going to have a much larger moment of inertia than this one has. So it's going to have a much larger tendency to retain its initial rotational speed. It's going to have a much larger tendency to resist rotational acceleration or rotational motion. All right, so a couple of things that we'll do. These are straightforward exercises because I want you to know how to pick the formulas for this one. And so assume that you got this sphere, the radius is going to be given. The mass is given. Mass is given, the radius is given. So figure out the moment of inertia. So the thing to do is just know how to pick out the formula. So it's going to be 2/5 mr squared. So that's what we're going to use. And then when you're done, you're going to end up getting kilograms per meter squared. All right, so this one was straightforward. So that's how you pick the formula based on that. All right, so now let's do one more simple exercise. This is regarding a bicycle wheel. All right, so a bunch of stuff is given. It's okay. Once again, we're looking for the moment of inertia. Decided that this should be the radius because I'm being lazy. All right, so I didn't want to divide by 2, and then that's where I forgot when I was doing the problem. So the mass is given. All right, so if it's a bicycle tire, the wheel, use the thin hoop. So it's going to be mr squared. So plug the numbers in, boom, boom, boom. So this one was straightforward. Okay, so now let's start to advance into more abstract and more interesting topics. All right, so here's your linear or tangential kinetic energy, whatever that means. Okay, so we're looking at the kinetic energy on the direction of rotation. So rotational kinetic energy is what we're looking at. All right, if it's a bicycle wheel or something, so it's going to have a tangential speed. Tangential speed could be expressed in terms of the rotational speed. So it's going to be r squared times omega squared that you got. So this mr squared that you're looking at, that's your rotational mass-like term, or rotational inertia, the moment of inertia. All right, so do back substitution. This is going to give you a rotational kinetic energy. All right, so rotational kinetic energy is the kinetic energy along the direction of the curve, or along the direction of the curvature. If it's a bicycle tire, it's the kinetic energy of the rotational kinetic energy of the wheel, so to speak. So that's your rotational kinetic energy. Okay, just throwing the terms around just like that, along with the mathematics and giving you some simplistic expressions, almost makes it look like you understand what's going on. But I got news for you guys. We will have to dig into this. This is not as easy as it is, okay? Because this tangential kinetic energy term that I'm using, that's the kinetic energy along the direction of the rotation of the wheel or the soccer ball or whatever something is spinning or rotating or rolling or whatnot. In the next discussion, we're going to take a different meaning. All right. And before, all right, let's move forward. Question number 10. All right, so we're looking at a centrifugal subrotor, just like that. This problem does something interesting. It gives you the, all right, so computer's gonna back out. All right, so it gives you the moment of inertia of this motor, and it asks you the amount of energy required for it to come to a stop. It's already moving at 8,250 RPM. So what is the amount of energy required to bring it to a stop? Hey, she went to that? Okay, yes, hold on. So what's the amount of energy required for it to come to a stop? Okay, this is the sort of stuff that can make it impossible to solve some of the physics problems in real life, because unless you have a really good conceptual connection to what the question is asking, it's really, really tough to find the right formula to solve a problem like this. Okay, so 90% of the work in problem solving in physics is being able to know how to start. I'm not kidding. All right. And unless you really have a really deep understanding of physics, you'll find it next to impossible to solve actual physics problems in real life. And I am trying to get you to have a bit of a taste of it. Because once you know which formula to start with, if you can justify your first formula, the rest is math usually. Okay, math is muscle memory. If you're practicing enough, it shouldn't be that big of a deal. All right, so how much energy is required to bring it to a stop from that RPM, that many RPM? What I'm saying is, what is the amount of work required? How much energy is required is the same as what is the amount of work which is required to actually stop it. All right, so I'm listing everything. And then I think how much energy is required to bring it from rest to the speed. Oh, evidently we're not stopping it, we're just accelerating. Okay, I misread the question. So the initial speed is 0 radians per second, and now final speed is going to be this many RPMs, expressed in terms of radians per second. So what is the amount of work required? The work is a process of transferring energy. So the only way you're going to be able to transfer energy is through work, in essence. So you need to make that connection. And the amount of energy which is going to be transferred to the system is going to be transferred to the system in the form of kinetic energy. And obviously, it's going to be transferred into the system in the form of rotational kinetic energy, in essence. All right, so which means that you have to use the work formula. All right, so the work is the amount of energy that gets transferred into the system, and the energy is going to be transferred in the form of kinetic energy. So you got the initial speed, you got the final speed. Initial speed is 0. All right, so this is the final expression, symbolic expression that we came up with. Plug the numbers in, come up with an expression in terms of joules. If it's joules, my preference is to express it in terms of calories, because calories is something that we can relate to. All right, so I got the key there. And that's it. So this is a multiple choice quality problem. All right. Okay, now the kicker. Because I'm going to come up with one extra term, total kinetic energy. What if you have something that's rotating? So it's got a rotational kinetic energy, like a rolling ball, or a car wheel, or a bicycle wheel. Okay, so you got this mass which is rotating, but at the same time, its center of mass is advancing horizontally. All right, so its center of mass is moving linearly. So which means that it's going to have two types of kinetic energies. Center of mass is going to be moving linearly, so which means that it's going to have a linear regular kinetic energy, which is known as the translational kinetic energy, which is 1/2 mv squared. And then there's going to be a rotation relative to the center of mass, so which means that it's also going to have a rotational kinetic energy. All right, so example of something that has both translational kinetic energy as well as the rotational kinetic energy is a rolling ball. All right, so center of mass is going to be moving at a given speed, so it's going to have a translational kinetic energy, and the ball is going to be rolling. Point of contact is going to be rolling relative to the center of mass, so it's also going to have a rotational kinetic energy. So at this point, you will have total kinetic energy. So total kinetic energy is a combination of translational, meaning that the kinetic energy of the center of mass, and the rotational kinetic energy, meaning that it's going to be moving relative to its center of mass. All right, so center of mass is the center of balance in this case. All right, so add on to these terms. Let's do a simple exercise first. All right, so we got a bowling ball. Its mass is given, its radius is given, converted to meters. Also, its speed is given in terms of meters per second. So calculate this total energy. All right, normally you would go kinetic energy of the rolling ball is going to be 1/2 mv squared. This is the way we used to do that. But we're only looking at the motion of the center of mass. Okay, so remember, every time I say geoforce diagram, you put a dot. Normally, if you're studying from a book, that would be the forces applied to the center of mass, or you always draw a ball, in essence, so you wouldn't miss it. So the forces are always applied to the center of mass. We were only considering the motion of centers of mass for all the masses. It didn't matter that you were an elephant or a four tempo. It didn't matter. Everything in my mind looked like a ball. All right, so it was a simplified expression of follow the center of mass, follow the center of mass. All right, so if that's the case, kinetic energy of the center of mass was 1/2 mv squared. Now, we're also looking at the motion relative to the center of mass. All right, this thing is rolling. So if that's the case, all right, so it's also got rotational motion. So what is its total kinetic energy if that's the case? So it's going to be kinetic energy of the translational motion or the linear motion. So you're following the kinetic energy of the center of mass, plus now you have to follow the kinetic energy relative to the center of mass of this rotational motion. All right, so now you got to add these terms up. Okay. Now I'm going to make a few points here and there. Okay, I'm not going to be mumbling it, but you will still miss it because this is the sort of detail that some of you guys have a hard time focusing on, and it's an important detail. All right, the important detail is going to be the difference between tangential speed and the translational speed. Okay, that'll come up. All right, so here, 1/2 mv squared is the translational speed. Translational meaning that's a linear speed. This is the linear speed of the center of mass. All right, and then this is the rotational inertia for the bowling ball. So this one is going to be 2/5 mr squared. So just ignore this portion. Let's focus on this portion. Okay, so I'm going to try to express the rotational speed in terms of the tangential speed. Okay, and then I'm going to make a few comments here and there. These comments are not going to be very crucial at this level, but those little things that I'm about to emphasize will become hugely important when you're taking engineering dynamics. All right, our school is supposed to offer it at some point, but the engineering department is not up and ready as yet. They were supposed to have it up and ready by now, but hopefully it's going to happen by next fall. All right, that was one of the conditions of my accepting to work at the school, but we'll see what happens. All right, so 2/5 mr squared. All right, and you got omega squared right here. All right, so let's play with this. Okay, r omega is going to give you your tangential speed. All right, so r omega is going to give you your tangential speed. All right, so that's the speed on the curvature. All right, when I was focusing on this, guys, this is a recording from a lecture. So I was focusing on this one, and it's a late night lecture, obviously. So all of a sudden, I stopped focusing on the left hand side. So this should be mv squared that you're looking at. So I'm going to make a correction there shortly because I came up with mv squared here, and then I just want to combine the v's, and then of course these are v's as well. Okay, so here's my abstract argument for this one. That will become crucial when you guys are taking engineering dynamics. All right, the course that I taught for like 10, 15 years as well at one of the community colleges in Chicago. All right, so this is the tangential speed, and this is the translational speed. All right, so this is the speed of the center mass, and this is this tangential speed right at the rim. Okay, guys, just think about it. You know, the speed at the rim, or speed at the rim if it's a bicycle tire, or speed at the edge if it's a rolling bowling ball, is going to be the same as the tangential speed. This linear speed is going to be the same as the speed of the center mass. As a result, you can combine these. Obviously, both of them will be the same speed. It's the same mass. All right, so now you got common terms. All right, so if you didn't understand that argument, not a big deal. It just, you need to know that the speed at the edge, at the boundary, at the contact point is exactly the same speed as the center mass. All right, so the translational tangential speed of the tires is exactly the same as the speed of the center mass of the car. Okay, so just understand that. Tangential speed of the tires cannot be larger or smaller than the speed of the center of the car, or else the wheels would be moving faster or slower than the car. That doesn't make sense. All right, so we end up coming up with the total kinetic energy of the bowling ball, and notice that the total kinetic energy of the bowling ball is going to be more than 1/2 mv squared because of the rotational motion. All right, so the number is not that important at this point, but understand that if you include the rotational motion, the total kinetic energy is going to be more than the kinetic energy that we used to consider previously. All right, now, okay, so let's do a simple exercise of 14. All right, so we got this pole, it's being balanced at it's going to be balanced vertically on its tip. All right, and then it's going to start to fall, and the lower end is not going to slip. So the question is, what will be the speed of the upper end? So we're looking at the tip of the pole just before it hits the ground. And then it says hint, use the conservation of energy. All right, so we got this pole. It's going to be moving relative to its point of rotation, which is located right here. All right, so this is the length of the pole. I'm going to use L for that. Okay, Jonathan, just hold on to that one. Okay, because that was one of the conditions of me accepting the job offer. Because unless the physics is going to be competitive, I can obviously I don't want to work at a place where there's no future. So just hold on to that one. Okay, because I've been told differently, so just hold on to it. All right, so we got a pole. This is the length of the pole. And okay. Anyway, so what are we looking at? All right, so we're trying to figure out the speed of the tip of this when it hits the ground. Okay, so this seems like a bit of an exercise, and it is a nice little exercise, but this is going to turn into a bit of a mind twister shortly because there's a story behind it. All right, so let's figure out its speed at the top. So what is the speed of the tip of the pole? So the length is given. Speed is what we're looking for in terms of miles per hour. And so here's the acceleration due to gravity. So because gravity is the only force acting, we will assume that the mechanical energy is conserved. So here's our initial mechanical energy. Here's our final mechanical energy. Okay, now it gets interesting. Okay, so okay, this is not going to have any sort of linear motion, but it's going to have rotational motion. So this initial potential energy related to the height of this point, and because this thing is moving relative to the, I don't want to say center of mass, but it's moving relative to the center of rotation right here, point of rotation here. So it's going to have rotational kinetic energy, right? All right, so as it's tipping over in this direction, as it's tipping, so its gravitational potential energy is going to turn into the rotational kinetic energy right at that point. All right, so rotational kinetic energy term is here, and gravitational potential energy term is right there. All right, so the letter Y is going to represent the length. Height is going to represent the length of the pole. And this is I. All right, I put down M, but I'm going to make a correction. It's going to be I. All right, so I is the rotational inertia. Okay, so that's what we will get to use for rotational inertia. It's going to be 1/3 ml squared. And at this point, okay, so I'm doing the algebra, doing a lecture once again, and my solution is not going to be the fastest or the most elegant. But I mean, you can do it. You can do your algebra any way you want. You'll come up with the same answer. So, all right. So 2 times 3 is going to be 6. ml squared omega squared. I go, okay. So let me get rid of the m's. All right. So mindlessly, I'm just going to follow. I'm going to try to isolate omega first. So that's what I'm going to try to do. All right. So get rid of 6. Get rid of L. And then I come up with this term. And then what I'm going to do is I'm going to try to express this in terms of a tangential speed. All right, so tangential speed is going to be R times omega. R becomes L. So I'm going to isolate omega from here and do a back substitution there. Then I could have done this in 2 steps, but just not paying attention, I made it much longer. Again, cancellation among the L's. And then move L from left to right. Okay, this is the final term. Except I just made it really, really long. Okay, so and now I came up with an expression for the final speed. Tip is going to hit the ground at this speed, and that's going to be 26 miles per hour. Okay, so this was an interesting exercise. Okay, this is like a bit of a test following exercise. All right, and I'm looking for some to do a demonstration. All right, just want to use that, like the poll that you guys are looking at. All right, so let's make, there's a backstory here that I want to use. Just want to be able to see myself for this one. So let me just stop the PowerPoint. And all right, stop this. And then so you guys can see this. Okay. All right, so you got the tip of the knife. It's like a whole movie. All right, so you guys see the tip of the knife. All right, so if I were to balance this and then let it just tip over this way, all right, now you know how to figure out the speed of the tip. All right, so you let it go, gravity takes over, so potential energy turns into rotational kinetic energy, and then boom, you got the speed of the tip. Okay, so now the backstory that I want to discuss. I don't know, this is like 15 years ago or something. I'm visiting a friend of mine who's working at, happens to be a physicist and working as a computer scientist. And there was a real computer scientist at the department. So we were just having a chat, and then the guy goes, he said, did you know, he said, do you know that the tip of this knife, for example, this happens to be a knife, when it tips over, the tip is going to accelerate at a larger rate than an object falling from the same height. All right, so which means that if you drop an object from this height, and the acceleration of this object is going to be due to gravity, and then the tip is going to accelerate at a larger rate than the falling object. Okay, so as soon as he said that, I said no. I said that's nonsense. I was very reflexively, I said that's nonsense. Nothing can accelerate at a rate faster than gravity, because this is a formal free fall, so is this one. So the object falling from this height is going to be falling at the same rate as the tip will, and that's it. He said no. He said tip is going to have a larger acceleration. As soon as somebody says that, in physics we say prove it. Okay, and when we say prove it, we don't mean, hey, do a demonstration and then let's get some measurements or whatever. That's not what we mean. When we say prove it, we mean, hey, just put it on paper, show me a derivation of it. All right, that's the way we do it. So it's not that we agree with each other most of the time. In reality, people disagree with each other all the time, just like in real life. In physics, though, when there's a disagreement with a physicist, I go, okay, let me show you what I'm thinking. I would do the derivations, and then the guy would say, oh well, let me do it my way, and then they would do their own derivations. And that's what it is. Okay. And that's how it is done. All right, hold on. Just completely forgot. Yes. All right, I gotta respond to this real fast. Yeah. All right, I gotta check out something. I completely forgot that. All right, so this guy is a computer scientist, right? So there's absolutely no way he's going to be able to do a derivation of it. And so I was completely about to ignore this guy, obviously, because he's a computer scientist, he's not a physicist. And then he said something real weird. And then all of a sudden I go, wait a minute, there's something here that I'm missing, I think. He said that he's got his computer science degree from MIT, and he took his physics over at MIT. And all of a sudden I'm thinking, wait a minute, this guy's a computer scientist, and he's an MIT student, for God's sake. All right, these guys are not like the rest of us, in a sense. These people are somewhat gifted, and they pay attention to these weird details. He said he doesn't remember the derivation of the math of it, obviously, because it was like 30 years before, which is understandable. But he remembered the discussion that the professor made, and then he put a derivation up on the board. That was just so weird that's the reason why he remembered it, because he thought, just like I did, that the tip would be accelerating at the same rate. All right, that's what he did. And somehow the professor convinced him that that wasn't the case. And then I thought to myself, wait a minute, if it's doable, obviously this professor was able to do it, we should be able to do it ourselves, because intuitively I said that's not possible, but then again, I decided that we should probably try to replicate that. All right, so that's what I decided to do. Okay, so that's what we're about to do. Okay. Oh, it's working. What do you know? All right, multitasking here. Maybe I go something up. All right, so let's quickly do that. Okay, so it's related to the problem that we were just doing, so the case study. Okay, so we drop an object. It's going to accelerate in this direction. And then we're following the tip of this object. And of course, it's going to accelerate in that direction. We figured out the speed of the tip due to rotational motion. And then we'll take a look at the final speed of this object that we dropped. All right, so if I'm right, they should have the same speed. If he is right, all right, this should be moving, the tip should be moving faster than for the following object. So if the tip has an acceleration larger than the gravitational acceleration, tip should be falling faster than the acceleration due to gravity. All right, so the free fall is straightforward. Initial form of energy is going to be potential. The final form of energy is going to be all kinetic. All right, so mass is not going to matter. And the length is the height of that ball. So this is the final speed of the ball. And in rotational motion, okay, so let's take a look at the speed of the tip. Initial final energy is going to be rotational kinetic energy. Initial energy is the potential energy of the tip. Instead of repeating the same calculation, I'm just going to cheat and just grab the work that we did before, and that's it. All right, so this is the speed of the tip of the knife that we're looking at. Notice that this final speed here is actually smaller than the final speed here. In fact, the rotational speed, final speed, is going to be about 1.7 times larger than the linear speed of a falling object. So which means that the rotational one is going to be accelerating at a larger acceleration and a larger rate than the gravitational acceleration. This was a learning experience, all right, because I thought I understood the concept well enough only to realize that this guy had a point. All right, this guy had a point. And all of a sudden, I noticed that this little discussion is the reason why the chimneys break somewhere near the center. All right, I thought this was really not that important, but it turned out to be fairly important. Because during the physics lectures, this is the sort of observation that I would never care for. So what's happening is up to the center of mass, the entire structure is going to be accelerating tangentially, or the component of the acceleration in the downward direction is going to be the same as 1g, and anything above this point is going to be accelerating at a rate larger than 1g. So one thing is to accelerate at a rate which is larger than 1g, they need to be pulled down in this direction. Okay, the reason it's got a center mass which is located here, I'm able to pull the rest of the structure at a rate larger than 1g because everything is rigidly connected along that side. So everything has a proper reinforcement on the side, all right? Anything that falls at a rate larger than 1g is not properly reinforced structurally along sideways. As a result, these things usually break apart. And all of a sudden, this falling chimney thing, okay. This one is the second mind twister. Okay, this one also a learning experience. This is the sort of stuff that you would think that you will learn when you're taking a physics course. And unfortunately, these are the sort of stuff that you learn either through teaching or sometimes something weird happens, like having that conversation with that computer scientist. And all of a sudden, I noticed that my understanding wasn't quite there. Because he said something that I disagreed with, he didn't know how to explain it. And next thing you know, I did the computation only to realize that, hey, it was right, I was wrong. And that was a really good learning experience. And all of a sudden, I noticed that only the center of mass, every single point up to center of mass is going to accelerate at a rate of g, and everything above that will be accelerating at a rate larger than g, provided that it is strictly reinforced along the sideways direction against shear, in a sort of shear. So that was a good learning experience. Okay, this one came out of an article that I read. I don't know, it's like one of those local newspaper articles, and the article was talking about a bunch of high school students doing a simple physics experiment. So they had a car driven out to a black ice, and then they would just lock up the brakes, and they were using a radar gun to figure out the speed. So, you know, the car is going to hit the black ice at 60 miles per hour or something. And then if you're using a radar gun, the speed should go from 60 miles per hour to maybe 59.99 something. Okay, ice is not going to generate a lot of friction. Okay, so that's what they were expecting to see. So the guy just drives on the black ice, and then he just locks up the brakes. So they're looking at the radar, and then the speed goes from 60 miles per hour to 60.11 or 6.12 miles per hour. So instead of speed going down, it just goes up slightly. So it was surprising to them. So they repeated the experiment a number of times, and they couldn't figure out why that was happening. And the high school teacher was completely confused there. Everyone was completely confused. All right, the whole purpose of the experiment was to figure out the coefficient of friction for ice. All right, so you have this little experiment. The car is going to slow down a little bit. And using the computations that I showed you how to do, you can figure out the coefficient of friction for ice Except for it to work, obviously the car was supposed to slow down a bit. Instead, the car just sped up. So how is that possible? Okay, let me tell you about my initial reaction. My initial reaction is exactly the same as your initial reaction. Oh, that's not what should be happening. All right, so if ice offers no friction at all right, you lock up the brakes, the speed of the car is not going to change. It's Newton's first law, inertia. In the absence of an external force, what should happen is the car should keep on moving at a constant speed in a straight line. So imagine that this is a perfectly frictionless surface. You lock up the brakes, the car cannot speed up. Okay, my initial reaction is they goofed up the experiment. A bunch of high school students, and they goofed up the experiment, and they just measured the wrong speed. And then I was very dismissive of it. And then I kept thinking about it. How could they mess up the experiment for guys? It's a radar gun, right? The only thing you're doing is you're following the guy, you're following the car at 60 miles per hour, hits the black ice, and then it skids into, well, the sun's black ice, he locks up the brakes. At that point, you can see the speed. Okay, there's no wrong measurement here. They repeated the experiment a number of times. Every time they did the experiment, the car sped up just slightly. Never slowed down by sped up. All right, and you could see the tires being locked up. It's not like this guy is accelerating. It's not hitting the gas pedal. The brakes are locked up. You could see the brakes just locking up. The wheel just stopped moving, and then the car speeds up. All right, so it just didn't make sense. It didn't make sense. I was just dismissive. I couldn't make sense out of it because it cannot be a measurement error. I cannot imagine how the car should be speeding up without an external force acting on it. And if there's an external force acting on it, it's friction, obviously, which means that the car had to slow down or it should be moving at the same speed in a straight line. That's it. So I was highly, highly dismissive of that. And then I'm lecturing regarding this topic. The first time around, it's like almost 20 years ago. Once again, it's engineering physics. And then I came to this topic, and I was just goofing around with it. And then all of a sudden, I realized that, of course, the car is going to speed up. All right, no one knew how to explain it. When I say no one knew, I meant the high school students and the high school teacher. And all of a sudden, I go, oh, there's something happening here, which is so neat. So here's what's happening, guys. All right, just let's focus on one wheel, all right, on black ice. All right, this wheel is going to have two different kinetic energies. It's going to have the kinetic energy of the center of mass. All right, so that's one kinetic energy. And it's also going to have kinetic energy relative to the center of mass, so that's the rotational speed. So it's got a tangential kinetic energy, and it's also got a rotational kinetic energy. Okay, so, and they add up to the total kinetic energy of the system. Okay, so the following one, despite the fact that there's a bit of math here, just listen to what I'm saying instead of worrying about the math. Imagine that this is a perfectly frictionless ice. Okay, there's no such thing, but just imagine, just follow along with it. Imagine that this thing is just so incredibly slippery that there's absolutely no frictional force acting on this. So, which means that the amount of work done on the tires will depend on the external force acting on the tires and the displacement, right? Excuse me. Displacement is along the horizontal direction. The force influencing the motion would be the frictional force opposing motion. But if you see that there's absolutely no friction acting on it, there's no work being done on the tire, so there would be no change in total kinetic energy of the system. So, which means that the total kinetic energy of the system before you engage the brakes and after you engage the brakes will not change. Okay, that's Newton's first law in essence. In the absence of an external force, the motion will be maintained. But now this is a little bit different, which means that there won't be any change in kinetic energy translated to the conservation of energy principle. So, which means that the total kinetic energy of the system before you engage the brakes and the total kinetic energy of the system after you engage the brakes will be the same. Remember, total kinetic energy is a combination of translational as well as the rotational kinetic energy, right? So, look, what happens when you lock up the brakes? When you lock up the brakes, kinetic energy is going to remain constant. Total kinetic energy will remain constant. What happens is the rotational kinetic energy is going to go to zero, all right? And which means that this rotational kinetic energy is going to get converted into translational kinetic energy, which means that this total rotational kinetic energy is going to get transferred to the kinetic energy of the center of mass, which means that the car is going to speed up just a little bit. So for a given constant total kinetic energy, if rotational kinetic energy goes down, translational kinetic energy is going to go up. So rotational motion gets converted into translational motion. As a result, the car is going to speed up. I've done the numbers, the calculations on this one. It's going to speed up fractionally, which means that the car is going to go from 60 miles per hour to 60.11 or 12 miles per hour. So the rotational kinetic energy of the tires will get transferred to the translational kinetic energy of the car. It gets transferred to the center of mass of the car. It's weird. And okay, so this is another thing that happens when you're taking physics courses. yeah, you do learn quite a bit, but through research, you do learn quite a bit more. And on top of that, when you're teaching, it's a different experience. When you're forced to explain stuff to other people, you understand it so much better. That's the reason why you have the conceptual portions of the task. And sometimes you guys say, I hear you guys say, well, you should give us more time, blah, blah, blah. Guys, everything that I ask you is everything that we discuss during the lectures inside out, okay? You cannot explain something that you don't understand. That's where it's at, all right? If you're having a hard time explaining something, the more than likely you don't really understand it, which means that you didn't really spend the time to comprehend it. When you listen to a lecture, it just feels like you get it, but when you try to explain it to someone else, and all of a sudden you go, oh, you didn't quite understand it. And this is one of those moments. All of a sudden I'm lecturing, I go, wait a minute, of course, if you lock up the brakes, the kinetic energy is constant, which is going to be constant in the absence of an external force because the friction is just so small. And all of a sudden you can see that this rotational motion is going to turn into translational motion. All right, so explain, learn to explain it to each other, to other people. And when you're forced to explain something, you'll understand it better. Because it's tough to explain something that you don't understand, obviously. And then you go, okay, so why is it that I'm having a hard time explaining it? The reason is because the understanding is missing. All right, lastly, the Geller's famous experiment. Incline experiment. Man, this incline experiment was interesting because he came up with the concept of inertia because he was trying to figure out the acceleration. He was trying to measure the acceleration due to gravity. And then out of that, we came up with a conservation of energy, not Galileo, but we did. Mechanical energy is something that physicists came up with during the 19th century because of Galileo's incline experiment. And so the Galileo's incline experiment hinges on the premise that the falling objects, because they fall at the same rate, they should probably roll at the same rate for us to be able to figure out the acceleration due to gravity. All right. So the question is, will they roll at the same rate? All right. So your test question is going to be related to this. This is, we're about to do a standard problem. All right, so in this case, we got a rolling ball. All right, so when it's rolling down, let me just conceptually say a few things. It's going to have two types of kinetic energies. It's going to have the kinetic energy of the center of mass, and it's also going to have kinetic energy relative to the center of mass. So it's going to have rotational kinetic energy. All right, so now that we said that, roll. All right, so case study. We got two cylinders. All right, so one is going to be a solid cylinder. The other one is going to be a hollow cylinder. So this one is solid, and this one is going to be hollow. All right, so they will have the same radius and maybe same mass. All right, so which one is going to reach the ground sooner? Okay, so according to Galileo, the premise of Galileo's experiment, because he was trying to slow the motion down, if his way of looking at it is correct, they should have the same acceleration and they should reach the ground at the same time, right? Okay, let's check to see if that's the case. So here's the initial height. All right, we'll assume that gravity is the only force acting, so which means that the mechanical energy is going to be constant. So here's the initial mechanical energy. It's a combination of kinetic and potential energies. Here's the final mechanical energy. So it's a combination of kinetic and potential energies again. One thing you need to remember is the kinetic energy is going to be a combination of rotational as well as the translational kinetic energy. Translational meaning that, once again, center mass is translating in this direction. It's moving in that direction. All right, so this is the rotational kinetic energy. This is the translational kinetic energy, which is 1/2 mv squared. This is related to the rotational motion. Potential energy is the same. It depends on the initial height. All right, so the final mechanical energy, two kinetic energy components, one potential energy component. This is the final height. Initial translational speed. It's related to the initial rotational speed and related to the initial height. So you got the kinetic energy terms, you got the potential energy. All right, looks kind of nasty, but it's not because we got a bunch of zeros that we plug in. All right, so initial rotational speed is 0, initial translational speed is 0, final height is 0, h is 0, so we've got a bunch of zeros that we'll get rid out. All right, so the math is simplified. Okay, so what else do we know? The rotational speed can be expressed in terms of the tangential speed. The tangential speed is the same as the translational speed. But before we do that, let's come up with a generalized expression that's going to have the rotational inertia in it. All right, so I'm expressing the rotational speed in terms of the tangential speed. Tangential speed is the same as the translational speed. All right, I'm factoring out the like terms, so v squared and 2 will be the like terms. And we're trying to figure out the final speed here. So v is what we are isolating. So multiply both sides by 2 and divide both sides by the expression inside the parentheses. Okay, so this is the final expression that I got, so get rid of the square. Okay, so this is for discussional purposes. Okay, so take a look at the speed and take a look at the moment of inertia. Okay, so the rotational inertia. Okay, so the final speed is going to depend on the rotational inertia. So what that means is unless the solid cylinder and the hollow cylinder, unless they have exactly the same moment of inertia, they're not going to have the same speed. So meaning that they're not going to have the same acceleration. So that's what it means. So you got this inverse relationship. The larger the moment of inertia is, the slower it's going to move at the bottom. So that kind of makes sense because the larger moment of inertia implies it's going to have a larger resistance to change motion, rotational motion. All right, so whichever the one that has a larger resistance to change in rotational motion is going to be moving slower. All right, so larger the moment of inertia is, the slower it's going to move. All right, so let's take a look at the cases. We got a hollow cylinder. It's got a moment of inertia. It's going to be mr squared. Hollow cylinder is the same as a rim in this case. All right, so let's do a back substitution. One thing that I want you to notice that the mass is not going to matter. Okay, so r squares will cancel out. And 2's will cancel out. The masses will cancel out. So the mass is not going to matter. The only thing that matters is the geometry of the mass. All right, so hollow cylinder is going to be moving at this speed. And then we have the solid cylinder. Solid cylinder is going to have a moment of inertia. It's going to be half of the hollow cylinder. All right, so once again, just do the back substitution. This is a moment of inertia, which is half of the hollow one, which means that this is going to be moving faster. So it's going to have a lower resistance to change in motion, rotational motion. So once again, the electrons will cancel. Mass is not going to matter, so it's also going to cancel. All right, we do a simplification. All right, this is a larger number for the solid cylinder than the hollow one. Hollow one is this, the solid one is this. 4/3 under the square root is going to give you a larger number than 1. So the solid one is going to be moving faster at the bottom of the incline, in essence. All right, but interesting thing is, okay, so a couple of things. Regardless, you can still figure out the acceleration due to gravity, regardless of this, if you could just measure the speed at the bottom. So the question is, how do you measure the speed at the bottom? Okay, today, piece of cake. We got radar guns and everything else to take down. In Galileo's day, no, right, that would not have been possible on this. All right, so his premise of slowing the motion down was the correct one, except at the end, I don't know how he could not come up with an actual number. He was able to come up with a relationship between the distance covered within each and every single consecutive time interval, but he was not able to come up with a value for G, obviously. All right, so that didn't really work out. All right, so the next question is, why is it that when it's a solid cylinder, its moment of inertia is smaller than when it's hollow? Okay, so what's causing that to happen? Because if it's a hollow cylinder, it's going to have a lot more resistance to the change in rotational motion than when it's a solid cylinder.
We're going to look at a couple more demonstrations of rotational inertia. Now, to review, rotational inertia is the property of an object that deals with a resistance to a change in its state of rotational motion. We know that this depends upon the mass of the object and the way that mass is distributed from the axis of rotation. For the first demonstration, let's look at this aluminum disc. This has quite a bit of inertia because much of the mass is distributed far from the axis of rotation. We're going to put this in motion with a motor and let it spin while we're doing something else, and it will take some time to spin down because of its large inertia or rotational inertia. So I'll get this thing going. I'll let it spin up here for about 5 to 10 seconds. And I've turned the motor off now, and now it's just slowing down. Now, it will slow down because there's frictions in the bearings. But it's going to take a while to do that because of its large rotational inertia. While that's happening, let's take a look at this demonstration right here. Here I've got 2 discs which have the same radii. One of them is an aluminum ring, and the other is a piece of wood. Now, if these have the same mass, they have the same inertia, but they don't have the same rotational inertia because that mass is distributed in a different way. For this, the mass is distributed uniformly throughout. For the ring, the mass is all distributed far from where the axis of rotation will be, which is going to be right through the center. And so this will have a greater rotational inertia than this wooden disc. What we're going to have them do is race down this incline. And the one with the greater rotational inertia will lose the race because it will have a greater resistance to a change in its state of rotational motion. Now, right now, the state of rotational motion of both objects is 0. They're not rotating. Once I remove the piece of wood, one of them is going to rotate more quickly. Let's see which one that is. So the wooden disc rotated more quickly and won the race down the incline. That makes sense because we said that the metal ring had greater rotational inertia, so there's a greater resistance to a change in its state of motion. It's going to have a smaller rotational acceleration as it goes down the plane. Let's take a look now at our disc. You can see that it's still turning. It's slowing down. It's almost stopped by now. But if we could make the friction in the bearings much, much less, this could continue spinning for a long period of time. If we made this a very large metallic disc, we could store a large amount of energy, rotational energy, in that disc, and we could keep that energy stored for a long period of time. Such devices are called flywheels, and they are used exactly for that purpose, for energy storage. Are demonstrations of rotational inertia. Now, to review, rotational inertia is the property of an object that deals with a resistance to a change in its state of rotational motion. We know.
All right, this guy did a really good job in explaining it. All right, so let's take a look at it from a couple of perspectives. All right, you got this solid block, cylindrical block. Okay, so then you have the rim. Okay, so he said, let's imagine that they have the same mass. So let's imagine that they have the same mass. I'm not sure if they do or not. He says they have the same mass. All right, so if they have exactly the same mass, they got the same inertia, right? But why is it that they don't have the same rotational inertia? Okay, so he did a good explanation for it. Rotational inertia, the moment of inertia depends on the radial distance of the mass relative to the point of rotation. Notice that if you have a rim like that, all the mass is located at a radial distance of r from the point of rotation. And if you have a solid cylinder, obviously the mass is going to be uniformly distributed all over the place. So the amount of mass near the point of rotation is going to have a smaller moment of inertia. And the moment of inertia gradually start to go up as you start to move away from the point of rotation. And then when you add all those moments of inertia, it's going to add up to a value which is going to be less than this, because it's the concentration of mass. So here, the entire mass is located at a radial distance r here, and here the mass is going to be radially distributed uniformly away from the point of rotation. All right, so as a result, what happens is the moment of inertia of this rotational inertia of this is going to be smaller than this. So the next question is, why is this half the moment of inertia of this one is? Well, that comes out of the derivation. How that derivation is done is something I'm going to show you shortly. But before I do that, make sure that you understand the concept. All right. So larger amount of mass is located at a radial distance away from the point of rotation is going to give you larger rotational inertia than uniformly distributed mass relative to the point of rotation. So conceptually, just keep that just for now. Okay, I'm noticing that most of you guys pick C. Okay, which is fine. I would have done the same thing. I think I'd probably pick the same thing regardless. And all of a sudden I'm thinking, no, I don't like it. There's a reason for it. Let me just run through my reasoning. Excuse me. So we got a solid sphere of mass as well as radius. It's rolling down without slipping because of friction. All right, so it's on an inclined plane starting from rest. The linear velocity of the sphere at the bottom of the incline depends on both the mass and the radius of the sphere, you would think, right? But now let's go back to what we did. At the end of it, though, okay, so it looks like it's going to depend on the mass and the radius of it. The mass and the radius of it is going to influence the moment of inertia here, right? All right, influence the moment of inertia. But moment of inertia, depending upon the geometry, it's always going to be some kind of a function of mr squared. So when you put mr squared into this, mass will always cancel, the radius is always going to cancel. So at the end, the mass is not going to matter and the size is not going to matter. The only thing that matters is the geometry. All right, at the end, look, when you finish up the computations, at the end, the only thing that matters is the geometry in essence. So it's not going to matter. All right, so this one is for a solid cylinder and the other one was for a rim. At the end, it really didn't matter. All right, so if this is solid, this is solid. And so it affects the moment of inertia. The moment of inertia depends on the size, but it's not going to affect the final speed. All right, so the correct answer for the multiple choice has to be D. All right, C is not the right answer. It's got to be D. All right, so let's do a lecture review, 600 minutes. All right, so let's finish this up. All right, so we will finish up the portions that we didn't do. Okay, so relationship between the moment of inertia and radius is going to be direct. So moment of inertia is always going to depend on the square of the radial distance relative to the point of rotation. The relationship between the moment of inertia and mass is going to be direct for a given radius. The more massive it is, the larger the moment of inertia is. So swinging a baseball bat, you can do it from either the narrow end or the more massive end. So it's going to be easier to swing it from the more massive end, right? All right, because this end is less massive. So it's going to have a moment of inertia is going to be relatively small. So it's not going to offer a lot of resistance to rotational motion. So less massive end is going to be easier to swing. So rotational kinetic energy is the same idea of linear kinetic energy, except mass becomes the rotational inertia and speed becomes the rotational speed. All right, so which will have a greater acceleration rolling down an inclined bowling ball or a volleyball? Okay, remember, the mass is not going to matter, right? Right, size is not going to matter either, as it so happens. The only thing that's going to matter is the shape, and they will have the same shape, except in the case of the bowling ball, the mass is going to be uniformly distributed relative to the center of mass. In the case of the volleyball, all the mass is going to be located at a radial distance away, so which means that volleyball is actually going to have a larger moment of inertia, so which means that the bowling ball is going to be moving faster at the bottom. That's what it means. The bowling ball is going to be faster at the bottom. All right, so I'm going to do a little bit of derivations at this point. Okay, let me just do it first and then tell you something about it. Okay, these are from engineering statics course that I was teaching. The reason why I spend so much time torturing you guys, trying to get you guys ready for engineering classes, and the reason why everything is so, I say get the concepts, and just use the math properly, which means that don't use numbers, just stick with the symbols, this and that. All right, the reason is because when you take this course over again at the next level, and when you take it, you'll be taking it at a university because our school does not operate as that. We're going to be taking engineering statics. I don't care what your major is in terms of engineering. It's electrical engineering, civil engineering, mechanical engineering. It doesn't matter. There are certain courses that are required. Engineering statics and engineering dynamics. Everybody has to take this. All right. Engineering statics is just based upon this chapter that we just covered and the next chapter. So out of these 2 chapters, they come up with 11 chapters. 2-dimensional motion becomes 3-dimensional, and make sure you have taken your Calc 3 before you take it because it's applied Calc 3, it's vector calculus. All right, so I got this weird looking mass, and I'm just spinning this mass relative to its center of mass. All right, so how do you figure out the moment of inertia at this weird looking mass? So what you do is you grab a differential mass element, which means that you grab the mass within a certain region of it, and then I'm just going to rotate it relative to the center of mass. All right, so this is the mass that's being rotated at this radial distance r squared. And then what I'm going to do is I'm going to grab a second small segment of the mass here, and then the third, the fourth, fifth, or whatever. And then I'm just going to add up these small differential mass elements. Okay, so the summation sign becomes integral sign in order to get the total moment of inertia of this thing. Okay, now we are using calculus. All right, and this mass may or may not be a uniform mass, uniformly distributed mass. If it's uniformly distributed, it's going to have a uniform density, which is rho, which is going to be, the mass is going to be uniformly distributed within the volume of the shape that you're looking at. So I'm going to take this mass, the differential mass, and express it in terms of its mass density and the volume that you're looking at. It's assuming that the mass is uniformly distributed. The rest is calculus right now. All right, so you take this out of the integral sign because it's a constant, it's not going to affect the differentiations. And then you say, hey, you know, I just came up with this weird shape. And if you want to really find the moment of inertia of this weird shape, I reduced everything into a single formula that you can use for different shapes, basically. So that's what I did. I came up with a generalized mathematical expression that's going to allow us to be able to find the moments of inertia of different geometries. Okay, so, and using that simplified expression, I'm going to try to figure out the moment of inertia of one of these shapes. I could do this. This is a standard engineering and physics problem, or you could do the solid cylinder. This is also a standard problem, or you could do the thin hoop. It's just, once again, these formulas came out of some kind of derivation, the simplified mathematical modeling that I just came up with. Okay, so evidently, the one that I'm going to do is this one. All right, guys, we're going to be going over time for like a few minutes. Just bear with me. All right, so I want to show you how to come up with this, because this is your future. I'm looking into your future, and so that you guys know what you guys are getting into. All right, there's a reason why I'm so strict with the mathematics, so you can see what happens. All right, so the moments of inertia of a cylinder. By the way, everything that I'm doing right now is everything that you're expected to be able to do on your own. They will give you different shapes, geometries, and they will want you to actually find the moments of inertia for each and every single geometry. And on top of that, in order to make it interesting, depending upon which school you go to, I don't know, you can go to a regular university average. They'll give you, if that's the case, that they will give you a constant density distribution, which is easier to do. If you go to a really hot, challenging university with a really top-notch engineering program, they will give you a non-uniform mass distribution, mass density. It's going to make it a little bit more challenging. All right, so because I'm not teaching engineering to you guys, I'm teaching the physics of it, so I'm just going to give you uniform distribution right now. All right, so whatever the book that I'm using divides the heights from the middle. It's just height is going to be h in this case, so r is the radius. All right, so this is the expression that we decided that we were going to use from engineering. So moment of inertia is going to be relative to the rotational axis. Rotational axis is lined up along the z direction. Okay, so the things that I'm emphasizing is, hey, look, guys, they're coordinate systems. Okay, I graded your last test today, or last two tests today, as I was grading it, I recorded it, and so just wait for the recording. It needs to be added in. You're missing these coordinate systems when you're solving these problems, which you cannot. Don't do that. All right, don't do that. You get penalized for doing it, obviously, because I want you to have the right habits as well. When you're setting up your forces, make sure that your forces are set up inside a coordinate system as well. All right, so I got the coordinate system. So the rotational axis is going to be the z-axis that you're looking at, and this mass, the differential mass, is going to be rotated relative to that z-axis. All right, so it's in this case the density that you're looking at, the mass density, is constant. So I'm just taking it out of the equation, and then in order to solve this problem, I'm going to do a couple of things. I'm going to use a simple trick that they will show you in Calc 2. All right. And when you're taking an engineering physics course, statics, they will also show you how to do this stuff using a little bit more advanced calculus. Okay, so what I'm going to do is I'm going to take the volume of this cylinder and I'm going to turn it into a differential volume. Okay, this is a trick that's really useful in solving physics problems. Once again, this is something that they teach you in Calc 2. All right, I don't know the system in Texas. I assume that that's universal. In Calc 2 is where you end up seeing it. So what I'm doing is I'm turning this volume into a differential volume. So when I'm expressing this as a differential volume, the volume is going to change. And the reason why the volume is going to change in this case is because the radius is going to change in this case. So you differentiate the left-hand side as well as the right-hand side. The right-hand side is going to get differentiated relative to the radial r. So if you take the differential of r, it's going to be 2r dr. All right, so it's going to be 2r dr would be the variable on the right-hand side. So I was able to take the volume expression for a cylinder, and I was able to express it in terms of a differential volume. And then I'm going to be able to take this differential volume and then substitute it back into this mathematical expression that you're looking at. And all of a sudden, this volume could be expressed in terms of the differential of radius. All right, so you got your original r squared, and then in the green, I got my differential volume. Differential volume is going to be expressed in terms of r as well. We've got a bunch of constants. Pi is a constant, 2 is obviously it's a number. H is not going to change, all right? And then I'm just going to be able to pull out my constants, pull them out of the integral sign. So what's going to happen, according to this, is the moment of inertia of this volume is going to depend on how this mass is distributed radially on the radial direction. So now what you need to do is you need to integrate r from center to the capital R, which is the radius. So r cubed dr is going to be r to the 4th power divided by 4. Do a back substitution again. All right, so evaluate this at the limits. All right, which we did. All right, so do a simplification. All right, so evidently I'm looking at the moment of inertia of a solid cylindrical disk. It looks like, okay, so that's what I'm doing. So now what we need to do is we need to express this in terms of the total mass. All right, instead of using the densities. So now we can express the total mass in terms of density as well as the volume. This is how it is done. And you know that the density is constant. The volume, we got a differential volume that we will get to use for that. Do a back substitution. Oh, this is so much fun. All right, so the radius is going to be evaluated. The r is going to be evaluated from 0 to capital R, which happens to be the radius of the solid cylinder. All right, once again, pull out the constants, pull them out of the integral sign. All right, so everything which is not going to change is going to be here. Now you have r dr, so this is going to be r squared divided by 2 when you finish up the in a row. All right, so you evaluate at the limits and then do a back substitution. Okay, so 2's will cancel. That was cute. All right, so we got pi, rho, whatever. All right, so now we came up with an expression for mass. All right, so express everything in terms of rho and do a back substitution into the original expression, which is located right here. And all right, so rho is going to be expressed in terms of mass. All right, so the like terms will cancel, pi's will cancel, h will cancel. We got r's to the 4th power here, so 4 and 2 will cancel. And we're done. Okay, so this is the moment of inertia for a solid cylinder, and that's how it is done.